Okay, so let me start the new stuff with just a couple of examples based on what we did last class. Um, so first, let's say that we have this beam that's fixed to the wall. So that's a fixed joint. This angle is 50 degrees. The length of the beam is 2 meters. And at the left end, the beam is connected to a cable that goes over a pulley. And that cable is connected to a mass of 200 kilograms. If the mass of the beam is 20 kilograms, what are the reactions at the wall? So I'm going to first draw a free body diagram of the mass so that we can figure out the tension in that cable. Who wants to just eyeball that and tell me what they think the cable tension is going to be there? It's going to be the weight of that mass. You have to be careful about that, though. This is the one way that this class gets you into bad habits that can make things difficult for you later. When there's no acceleration and a cable is just being loaded by a hanging mass, the cable tension is always equal to the weight of the hanging mass. So it makes it really easy. But once stuff starts accelerating, when you get into dynamics or whatever, if you try to make that assumption, it's going to make your answers wrong. That isn't true anymore. So that's why I tend to isolate the hanging mass and calculate that tension instead of just glassing over, because it can lead you to bad habits later. So, okay, free body diagram of the 200 kilogram mass. We have a weight of 1962. And then the cable force is up. I'll call that T. And so Newton's second law says 0T plus 0, negative 196.2 is equal to zeros. And so T is equal to positive 196.2 newtons. You can see from Newton's second law why you can't make that assumption if there's acceleration. If this was something over here, then T would not be equal to 196.2, or be equal to 196.2 plus something. Okay, and the bigger the acceleration is, the worse that approximation is.
Is supposed to be a decimal thing?
Yes. No, yes, you are correct. There is not. 1962. Okay, so now I'm going to isolate the beam. First, there's a weight. It has a mass of 20 kilograms. So where do we apply the weight? Center, yep. So 20 times 9.81 is 196.2 for this one. Then we have the cable force. That's straight up with a magnitude of 1962. And then what subtleties do we have to think about in order to determine what loads go at the wall? No thinking. You just go fixed joint, and then your brain is like processing, and then you're like full force vector and couple, and then you write it on there. Full force vector and couple. And no matter what the setting is, if you have a fixed joint, that's what you put in there. Okay, so now I'm going to write out the table. We have to choose an about point. Let's choose it up here. I mentioned, I think, last time that a lot of times it simplifies the math a little bit if your about point is where you have the most unknown forces. It doesn't make a huge difference, but might as well do it. So for that force R, what's the row vector? 0. I'm going to write it as 3 vectors still. The force vector is Rx, Ry, and everything's in a plane. Nothing's happening out of the plane, so leave that as 0. And so the cross product of these two gives you a 0 moment. And then at that same point, we have the couple MR. We don't care about the row vector or the force. So cross those out and then just put in MR. Then 196.2. The row vector we want is this, from the about point to where the force is applied. That's 1 meter of the beam. And the angle, well, this angle is 40. And so the angle of this whole thing is from the positive x-axis to here is 180 to get there, and then another 40, so 220. So 1 meter times cosine and sine of 220 is negative 0.643. What? 66? 40. Really? Wait, that doesn't sound right to me. I would say 642 and then 0.766 negative.
Sine is negative
643 and then negative 0.766.
Cosine 220 is negative 0.766. Sine 220 is negative 0.6.
I did it backwards? Yeah, okay. Okay, so negative 0.766, negative 0.643. Okay. And then the force vector is the weight, so that's 0, negative 196.20. And the cross product is 0.766 times 196.2. What do you get from that? Negative 150.3, and that's a z component. And then the last one is at the end of the beam. Um, the row vector we want goes from the about point to the end. It's just going to be twice what this one is. So what's that? 15.32, 1.532. Is that right? And 1.286, 0. And then the force vector is upwards, 1962. So 0, 1962, 0. And then the cross product is negative 1.532 times 1962. $1,578. Oh, 1,000. Okay. 3005.78. Okay. So now we go to Newton's laws.
So if we know that rho is just double, and then we know that the force is 10 times, I mean, isn't that answer roughly 20 times? Can you just...
Yes, you could do that.
It is linear?
That just didn't occur to me, yeah.
Okay.
Okay, so Newton's second law says add up all of these forces and set them equal to 0. So, and I'm going to leave off the z components because that's going to be a third equation that just says 0 equals 0. It's not helpful. So Rx, Ry plus 0, negative 196, 196.2 plus 0, positive 1962 is equal to zeros. And then the moment equation, now I'm only going to use the z components. So actually this one, let me rewrite that mr as 0, 0, mr, since I wrote everything else as vectors. So we have mr minus 150.3 plus 3005.78 is equal to 0. Yes. It should be positive, shouldn't it? And thank you. So yeah, we have a negative times a negative. This should be positive. And if you're careful, you can see that kind of stuff from thinking about the rotation that would be caused too. Like in this case, our about point is here. So wherever the about point is, imagine that being a hinge, like the thing's free to rotate around that point. If you applied a downward force, like imagine this is free to rotate and you tapped right here downward with a hammer, it would cause a counterclockwise rotation. And so that has to be positive. And that means that the other one's wrong too, the sign. We got a negative here, so mathematically it should have come out negative. But also if you think about it physically, if that's the hinge, you tap upward with a hammer, it gets it rotating clockwise, which is negative. So this one's positive, this one's negative. Any other questions? So positive, negative, And so now we can write this system of 3 equations, set it up to put into the reduced row echelon form. So the first equation says Rx is equal to 0. The second equation says Ry is equal to, what's 1962, or what's negative 1962 plus 196.2? Okay, so we already know all of that R vector. And instead of reduced row echelon form, in this case, we can just solve it all. So the third equation says MR is equal to 3005.78 minus 150.3. 2855.48. And the units here are Newton meters. Any questions about that? Okay, let's take the quiz.